Lewis structures are all about visualization of valence electrons, seeing them in both atoms and the interactions between atoms, because it's those interactions that allow us to visually see what's going on with the electrons in our different types of bonds. So when we deal with individual atoms, remember that there's a couple of steps. You have to recognize the symbol, you have to recognize the electron configuration. So when we look at carbon, since we know each side of the symbol is going to represent our orbital, and we know that we're dealing basically with 8 because of our S and our P. Remember, S is 2, P is 6. That's where we get the whole idea of 8. We want to go through and do this. So our first thing is to recognize our symbol for carbon is C. The next thing is to recognize the noble gas configuration, meaning you need to recognize the row it's on, you need to recognize the block it's in, and you need to recognize the previous noble gas. Again, remember that we looked at the row 2 because carbon's on row 2. We were 2 into the P block, so that was 2p2. If that's where my last electrons are, I know everything below is full, hence 2s2. The previous row's noble gas was helium. So that's where we get helium, 2s2, 2p2 as the valence for carbon. I'm sorry, from that we get the valence for carbon. That's the shorthand configuration. 2 is the highest number, so 2 plus 2 is 4, so that means I better have 4 dots around my carbon going in a clockwise fashion, and carbon's done. Whoops. Now, please do bromine. So, step 1, Br. The noble gas configuration is 4s2, 3d10, 4p5. Pause it, check what you think the valence electrons, draw the dots. So you should have picked up on 4s here, 4p here, so that means I have 5 and 2 is 7, so I have 7 dots around bromine. So basically we're getting all the reminders of the stuff we just talked about in terms of defining or determining our valence electrons from our noble gas configurations, recognizing all the clues that we are given in our electron configurations, both in terms of our periodic properties where we have loosely held versus tightly held electrons, what this means in terms of the valence, whether they are given or taken, the subsequent charges produced in those ions if I have a complete transfer of electrons, and that ultimately when we look at this we're taking advantage of or finding a trend in that we know the valence electron is going to be predicted by its location in the periodic table, because all I care about ultimately are the S and the P blocks, because that's 2 plus 6, that's where we get the magic number 8. And that give and take of electrons is based on those electronegative differences, and the electronegative difference is what determines whether electrons are transferred or shared. So in Lewis structures, I want to draw the Lewis structure for each element. I want to be able to show the transfer of the electrons with, again, an arrow, so that if I show that change, I then show that transfer of the electrons. If I've shown the transfer of the electrons, then I can draw the two ions together, remembering that it is the charge of opposites that creates my ionic bond. Now, the one thing I want you to do is whenever you do this, I want you to then make sure you take your brackets, okay, and I'm going to do it in red so that it's clear. I want you to draw brackets around the ion or the element that has all of the valence electrons. It has an overall charge of 1 negative. My sodium actually has a charge of 1 plus. I ran out of room, but you would put it to the right here. Leave yourself a little space. And this is always how I want you to do it. So you need to show the transfer, and then you need to show the subsequent formation of ions. For molecules, however, we have a whole complete different set of rules for counting or figuring out how to draw our molecules in Lewis diagrams. Now, when we do this, there's actually a series of 6 steps that we're going to go through first. First step, you have to count the total number of valence electrons. The second thing you'll do is then determine your central atom. Now, the central atom is what we put in the middle and we put the other ones around. How we recognize the central atom, it's unique, i.e. it's the only one there, or if there's only one of several, we choose the least electronegative element. From there, we then arrange the other atoms around it in a skeleton. So, an example. So, I'm going to take, carbon tetrachloride, CCl4. I know that carbon has 4 valence electrons. I know that chlorine has 7. I have 4 chlorines, hence the times 4 for 28. I add all that together, I get 32 total valence electrons. Now, carbon was my central atom because it was the unique, plus it is the least electronegative. I have now arranged my other chlorines around it as a skeleton. So our next three, we're looking to connect as bonds. So we want to connect all of the bonded atoms in the skeleton with a single bond, keeping in mind that each of those bonds represents 2 electrons, and I have to subtract that from my total. So let's look at what we have so far. So I put in my bonds, I put in a total of 4 bonds, that's 8 electrons. I now have 24 electrons left. Now, any remaining electrons, I satisfy the octet around the most electronegative atom first. In that case, the most electronegative atom is going to be my chlorine. And in order to do that, I'm now going to take my 24 electrons and put them around my chlorine atoms. Now, that means I have to satisfy my octet rule. So in order to satisfy my octet rule, I need 6 more electrons on each. So there's 1, 2, 3, 4, 5, 6. Well, the nice thing is I have 4 atoms. They need 6 each. That's going to account for all 24 electrons. So there's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, and everything has an octet, and I've used up all of my electrons, and I'm good. So the question arises though, what happens when I don't? So our what ifs. Our what ifs have 3 different categories. What if we run out of electrons? What if I have extra electrons? And then what if we have a central atom that breaks the octet rule? Okay, so the first example we're going to look at is one where you will have extra electrons. Notice what you do with extra electrons. Extra electrons always get put on the central atom. It doesn't matter. If I run out of electrons, that's when I have to start recognizing that I am still having to fulfill an octet, and that's when we start looking and discovering we have double or triple bonds involved. And if I have a central atom that is greater than 15, remember this is phosphorus, because phosphorus is element 15, so phosphorus plus, I can have more than an octet around it. So our first example is going to be arsenic triiodide, or ASI3. I count my valence electrons, 5 in arsenic, 7 in iodine. That gives me a total of 26. Arsenic is the center because it's the only one. I put my 3 iodines around it, and I'm going to draw my bond. So a skeleton along these lines. Now notice that I used 6 bonds, so 1, 2, 3. Or 3 bonds, I'm sorry, 2 electrons each, that's 6. Now I have 20 electrons left. I'm going to place these electrons around my 3 iodine atoms first because they are the most electronegative. 2, 3, 4, 5, 6 until you get done. You will notice there's only going to be this 18 electrons are accounted for. That means there's 2 electrons left. I didn't run out, so I don't have to worry about double or triple bonds. All extra electrons go on the central atom. So I'm going to cheat, 2, 4, 6, 8, and then my last 2 right there. So that's what it looks like. I put my remaining 2 electrons on it, whoops, and there and there. Now arsenic has an octet, as do all the iodine atoms. So again, 2 extra electrons, I place them around it, it looks like that. Now, you guys need to do CH2O. You know there's 12 valence electrons. Okay, carbon is my odd man out, but even though I have a carbon and an oxygen each, carbon is the least electronegative, so I'm going to draw lines between my H and my O. So here's what it looks like. So I have my skeleton done. I know I used 6, I had 12 to begin with. So now I look and I place the electrons around my oxygen atom first because it's the most electronegative. You should notice we run out of electrons before carbon has satisfied its octet. Now if I run out, that means I have to have a double or a triple bond. So because I ran out, what I'm literally going to do is I'm going to steal 2 electrons right here, and I'm going to create a bond right here. Now I have 1, 2, 3, 4 around my carbon. Oxygen has 2, 4, 5, 6, 7, 8. Hydrogen's good because they only needed 2. So there's no unshared electrons. Hydrogen can't form the double bonds. That's why it has to be between carbon and oxygen. What's cool is we can also do Lewis dot diagrams for polyatomic ions, and our rules have not changed. They're still covalently bonded, so we follow all our rules. We do have to account for the positive or the negative charge in our total electron count for our total valence electrons. So I'd like you to pause the video here. I want you to give me the Lewis dot diagram for chlorate. So first things first, you should have counted your valence electrons. Chlorine has 7, oxygen has 6, there's 3 of them, 7 plus 18. Notice here the plus 1 because of the negative charge, so I have 26 total. Chlorine is in the center because it's the odd man out. The oxygens should have been arranged around it. You should have drawn bonds from oxygen to chlorine. That means you had 3 of them. That was 3 bonds, hence 6 electrons. You now have 20 left. You should place the remaining electrons around the 3 oxygens to satisfy the octet. You should notice there are 2 electrons left over. If I have leftover electrons, there's no multiple bonds. The last 2 electrons have to be placed on the central atom. Now, the one thing we didn't talk about that you do notice now is that whenever you do a polyatomic ion, you always place the entire structure in brackets. And we put the charge on the outside, so you get this as your final, what it should have looked like. So, in summary, we know that the structure of a molecule or polyatomic ion can be represented by Lewis dot diagram. It's going to show the pattern of shared and unshared electrons, and 2 atoms can sometimes share more than one pair of electrons, forming a double or a triple bond.